Welcome back to ECE 320A. In this particular video, we're still working in Chapter 13, the first part of Chapter 13. And what we want to do is walk through a little bit more involved circuit analysis problem in the S domain and see how we would set that up, put that into the matrix formulation, and show how you would mechanically solve that, or at least set it up to be solved. Here is the circuit that we want to examine, and in this particular case you can see that we have several energy storage devices. We have 2 inductors and 2 capacitors. We have 4 resistors. We have a couple of sources. The one current source is actually going to open up at time t equal to 0, so that particular current source is establishing or helping to establish at the initial conditions. And in fact, we want v sub 1 of t to have 2 different functional forms determined by what happens at this transition of t equals 0. Prior to time 0, we want v sub 1 of t to be constant with a magnitude of 1. After time t equals 0, so that's going to play with this 5 amp current source to establish the initial conditions. And notice that this current source is a constant. This v sub 1 of t is a constant prior to t equals 0. So we will have initial conditions associated with these energy storage devices. And in fact, since they're DC sources prior to t less than 0, we know that the inductor currents will, the inductors will act like shorts, and the capacitors will open up, and we will then just have open circuits where we have the capacitors. What we want to do then is figure out how can we find the initial conditions on our energy storage devices, and we should have 4 different initial conditions. Then we will use those initial conditions to find an equivalent S-domain circuit for this circuit, and then we will need to worry about what the voltage v sub 1 of t is doing beyond t equal to 0, or for non-negative values of time. So now we need to take cosine of 5t as our source. The current source will be gone, and we'll then just have one source operating or functioning after time t equals 0. In this particular case, I hope that you can see that the omega, if someone asks you for that information, the omega, if they didn't tell you what it was, and if they gave you what t was, or if you could measure this period of oscillation, then that period t would have to be such that 5 is equal to 2 pi over t. So that you could find the frequency of that cosine waveform either by somebody telling you what omega is, or if they sketched this waveform and you could physically measure the period of that waveform. In this case, if you measured that period of the waveform, then you would want 2 pi over capital T to give you a result of 5. So in that case, T, if we solved for it, is now 2/5 pi, or 40% of pi, if we needed to, if we were actually measuring that. So let's now try to identify the initial conditions that exist for each of these energy storage elements. And to do that, let's now redraw this circuit for time less than 0, because it's in a steady state. It's been in that condition for an infinite amount of time. We now know that if we have DC sources, we have our inductors shorting and our capacitors opening. So let's now resketch this circuit with the inductors as wires and the capacitors as open circuits. And we also will have this 5 amp current source in play, which is actually going to be in parallel with this 8 ohm resistor, and we will also have this voltage source on the far left having a constant value of 1. If we re-sketch that circuit, then the top capacitor opens up and there's no current flowing in this particular branch. This particular capacitor also opens up, and we're now left with a circuit that looks as given. So now what we want to do is try to find these currents and voltages, and that will provide us with the 4 initial conditions that we need. And in fact, I hope you can see that the inductor currents actually have the same initial condition, and there we have a value of 1 on that voltage source. If we examine this circuit, we can actually see that if we now applied a KCL at node A, then we should be able to find all of these voltages and currents from that. And node A now, let's say, has a voltage of V sub x. So KCL at A now says that we can write this as, let's say we want to know this current. That current now is going to be V sub x minus 1 over the impedance between V sub x and this voltage source on the far right, which is the sum of those two resistors, 1 plus 2. So now we're dividing by 3. Then we could say that we want to know what's this current, and that current now is V sub x over 8. Those two currents exiting node A must equal the current coming into node A, which is 5. Or we can now hopefully see that, well, we could start playing with this a little bit. We now have 1/3 V sub x minus 1 plus 1/8 V sub x is equal to 5. We could multiply both sides through by 24 if we wanted to, without changing anything. And maybe before we had, well, it doesn't really matter. I guess I could have subtracted or added 1/3 to both sides before I did that. Why don't, it doesn't really matter. So now let's do that, and we now have 8 V sub x minus 8 plus 3 V sub x is equal to 5 times 24, which 5/4 is 5 times 25, that's 125, and we're not quite there. We're 5 less than that, so that's now 125 minus 5, which would then be 120. So that now we have 11 V sub x is equal to 128, or in fact, V sub x is now 128 over 11. And once we have V sub x, now we can use that to solve for a lot of these unknowns, in particular the currents and these capacitor voltages. For example, I sub L1 of 0, which is this leftmost current, we could say is 1 minus V sub x, where the 1 is the voltage on the left, divided by 3. So I sub, let me change colors, we now have I sub L sub 1 of 0 minus is now 1 minus V sub x over 3. And if we plug all of that in, we end up being, and v sub x is now 128 over 11. We end up with minus 39 over 11, and you can also see that that's equivalent, since we have open circuits on the capacitors. I sub L sub 1 is the same current as I sub L sub 2 prior to t equals 0. So there's now our inductor initial condition in both cases, and those currents are both defined positively going from left to right with a value of minus 39 over 11. So just keep track of that. We're saying it's going from left to right with a value of minus 39 over 11, which in fact says that it's going in the opposite direction. But let's just keep all of our defined currents and numerical values consistent. Let's now try to find v sub c sub 2 of 0 minus, and we can do that by writing a KVL equation around this particular mesh. So now we have this voltage drop, v sub c sub 2 of 0, that we will be solving for. If we write KVL now around that particular mesh, we have minus 1 going into the negative terminal of our source, plus I sub L sub 1 of 0 minus times 1, which is the resistor value, plus V sub C sub 2 of 0 minus is equal to 0. And now we know that I sub L sub 1 of 0 minus is minus 39 over 11. And that allows us now to solve for the only unknown in that one equation. V sub C sub 2 of 0 minus is now 50 over 11. We have 3 of our 4 unknowns. Now we need to find V sub C sub 1 of 0 minus. And we could find that by simply writing a KCL in different ways, but let's just say that we write it. I wanted to use a highlight, so let me go ahead and erase that particular line. And if we go around this way with our KCL, for whatever reason, that's what I'm wanting to do. Now I have minus V sub C sub 1 of 0 minus plus 2 times I sub L sub 2 of 0 minus is equal to 0. Again, I sub L sub 2 of 0 minus was this minus 39 over 11. So now we know that V sub C sub 1 of 0 minus is 2 times that, or minus 78 over 11. And those are now our 4 initial conditions on our 2 inductors and our 2 capacitors. That was obtained by examining that circuit prior to t equal to 0. And since we're doing the one-sided Laplace, now we can focus on what's going to happen in our circuit for t greater than or equal to 0, and we are interested now in the S-domain equivalent circuit. So that everywhere, and if we want to do mesh analysis, let's say that we continue with this thought process of doing mesh analysis, now what we need to do is simply re-sketch that circuit. And if I do that, let me sort of do it in stages. I'm going to go ahead and fill in the resistors that I know exist because they haven't changed. And they come through unaltered in the S-domain circuit. We also have a source over here, and it was a cosine in the time domain. Now we need to Laplace transform that cosine, which is s over s squared plus omega squared. This is now s over s squared plus omega squared. Omega was 5, so we have s over s squared plus 25. This is 1, this was 5, this was 2, and this was 8, and we no longer have to worry about that current source. It disappears for non-negative values of time. But we do need to worry about the capacitors and the inductors and incorporating their initial conditions, and we want to do that to preserve the mesh analysis, or these three meshes, which means that we want to incorporate the initial conditions as voltage sources. So if we look at this second inductor, it's now S times L. That particular inductor had 3 henries for its L, so we now have 3S, and we have a source. And in this particular case, we had a positive current from left to right, and we then know that the polarity is minus plus, with the magnitude being L times I sub L sub 2 of 0, so this is now 3 times minus 39 over 11. We also had a capacitor here that has an impedance of 1 over SC, and that capacitor had a C value of 5. We again want to put a voltage source in series with that impedance, and the polarity of that is consistent with what we had derived in the previous lecture. And this particular impedance then, voltage source is going to be determined by the initial condition on that voltage, which was V sub C sub 2. V sub C sub 2 is 50 over 11, and we need to divide that by S. So here we have 50 over 11 divided by S. There's the initial condition of capacitor 2. So we're sort of going in reverse in terms of how I've labeled those. Then we also have our first capacitor, which has an impedance of 1 over SC. It had a C of 6, so down here we have 1 over 6S, or 1 over S6, and the polarity now, to be consistent with how we had labeled the voltage before, from plus to minus, now needs to be plus to minus here, and that's now V sub C of 0 V sub C sub 1 of 0 minus, which is minus 78 over 11 times S. And finally, we have our first inductor, which had an inductance value of 4, and we now, to obtain the impedance, just scale that by S. So now we have 4S, and we have a source. And the source now needs to be consistent with the direction that we had defined the positive current, and that's now minus plus, and it's L times I sub L sub 1, so we now have L, which was 4, and I sub L sub 1 was minus 39 over 11. And now we have all of our initial conditions incorporated. Now we have 5 different sources to contend with. We have generalized impedance values, which means we have impedances that are functions of this complex frequency variable S. And now what we want to do is we want to write the mesh equations associated with this circuit. And in this case, we have 3 meshes, and we can now, let's be consistent with the direction that we make those mesh currents. That's important if we're going to write these equations by inspection. They all have to be going in the same clockwise or counterclockwise direction. Let me call this I sub 2 of S. And this current, again in the clockwise direction, is I sub 3 of S. And what I can do now is I can write a generalized Ohm's law in matrix form, and you should expect then that your equations are going to be something times your unknown currents, and you have three of those. You have three mesh currents. You have a lot of sources that are impacting those currents. And now you have something I is equal to, and all of these sources are voltages. And that's really just one column, but how many rows do we have? Well, we should have three mesh equations, so we have three equations in three unknowns. Here is actually going to be our impedance matrix, which dimensionally is 3 by 3. And what we want to do now is solve this for some particular unknown, and I'm not sure what we even started out wanting to know, but let's say that we wanted to solve for the second mesh current in this particular example. We now would need to either invert that 3 by 3 matrix that's a polynomial in S, which will now be rational expressions in S, and we would then find formulas for I sub 1, I sub 2, and I sub 3, and we could inverse Laplace transform each of those. Let's just focus on performing one such analysis, meaning suppose that now we wanted to solve for I sub 2. Here are the equations. We have Zi equal V. That's just Ohm's law. V is equal to Ri. R now has been generalized to an impedance. So this is a generalized Ohm's law. Z is made up of a matrix of rational elements in the complex frequency variable S. That means we have 9 elements sitting in Z since it's a 3 by 3 matrix. I is our vector of unknown currents, and that's a 3 by 1 vector. That product, 3 by 3 times a 3 by 1, gives us a 3 by 1 vector, and that's equal to the voltages, where those voltages are either the original applied voltage V sub 1 of t that we've now Laplace transformed, or voltage sources due to initial conditions. If we write these equations by inspection, which I hope we're starting to get comfortable with, we can actually do that in this case very easily by inspection because we do not have any dependent sources in the circuit. So that now if we maybe I should collapse this and I'll be toggling back and forth. Here is now our circuit. And what we want to do now is write that in a matrix form. Z times I is equal to V. And how do we do that? Let's focus on the diagonal terms. The 1, 1 diagonal is going to be associated with those impedances that touch the first mesh current, which is now 4S, 1, and 1 over S, or 5S. So let's see now if that's what we came up with in terms of our 1, 1 entry in this impedance matrix, and in fact it is. Let's look at the 2, 2 entry in our impedance matrix. That's going to be made up of the impedances that are touched by I sub 2. So as we go around the second mesh, we now are going to touch 1 over 5S. We're going to touch 3S. We're going to touch 2, and we're going to touch 8. Those all now need to get summed, and in our 2, 2 entry, we should have 1 over 5S plus 3S plus 2 plus 8. Finally, looking at the last diagonal entry, we need to worry about what I sub 3 touches in terms of its impedances. It touches 5, 1 over 6S, 2, and 3s. And that will now be the 3, 3 entry in this 3 by 3 impedance matrix. So we have 5, 1 over 6s, plus 2, plus 3s. How do we get the off diagonals? Now we go back to our circuit and we say, okay, what impedances are shared between these paired mesh currents? Do we have any impedances that are touched by both I sub 1 and I sub 2, or I sub 3? Do we have any impedances that are shared between I sub 1 and I sub 3? And there are no impedances shared, so we'll have zeros in the entries associated with the first mesh and the third mesh, or element location 1, 3, and 3, 1 in our Z matrix. That's now this 0 and that 0, because I1 and I3 did not have any shared impedance values. What about the impedance shared between I1 and I sub 2? Here's the impedance shared by I sub 1 and I sub 2. That's 1 over 5s. And now when it's shared, we just change the sign on those particular coupled entries. In this case, it's the entry in our Z matrix that's shared by 1 and 2, so that's element 1, 2, and element 2, 1. And those are going to be with a negative sign, so we now have minus 1 over 5s in both of those entries. We almost are finished with filling out our impedance matrix. Now we want to ask or examine what is actually going to be shared between I sub 2 and I sub 3. Now we have this impedance and that impedance that are shared by I sub 2 and I sub 3. So the sum of 2 plus 3s, or 3s plus 2, we negate that in entries 2, 3, and 3, 2 in our impedance matrix. Down here then we have 3s plus 2 negated, and minus 3s plus 2, the quantity, minus the quantity 3s plus 2 in the 2, 3 entry, and the same expression in our 3, 2 entry. That's our impedance matrix, and that now multiplies the currents I1, I2, and I3. The remaining right-hand side now needs to be found from how the sources either encourage or discourage currents, the mesh currents I1, I2, and I3. So, if we look at the first mesh, we have 3 different sources associated with that. We have our applied source, s over s squared plus 25. We have our source due to one of the inductors, and we have our source due to the capacitor. I don't remember which capacitor. I think it's the second capacitor. Now we want to ask, do those, if we increased those particular voltages, would they serve to encourage or discourage I sub 1 getting bigger? The s over s squared plus 25, if we increase that, that's going to make I1 bigger. So that will come in with a positive sign. The 4 times minus 39 over 11, just keep that as a quantity and say, okay, that now, if it increases, it would also make I1 increase, so let's add that algebraically with a plus sign. And finally, our capacitor's voltage due to the initial condition, 50 over 11s, if we made that bigger, that would actually serve to reduce I1, so we now subtract 50 over 11s from our equation on the right-hand side dealing with the first row. Or we now have s over s squared plus 5 squared plus 4 times the quantity minus 39 over 11 minus 50 over 11s. What about current I sub 2? Well, in this case, If we increase that voltage source, that would serve to increase I sub 2. If we increase this voltage source, that likewise would serve to increase I sub 2. Both of those now need to be algebraically introduced with positive signs. So that now we have a plus 50 over 11s plus 3 times a negative 39 over 11. Don't worry about the signs inside the particular voltages. Let's just worry about how we are introducing those algebraically into the right-hand side. Finally, then, dealing with the sources associated with I sub 3, now we have this source due to capacitor 1 and this source due to inductor 2. Let's look at capacitor 1's voltage source. If we increased that, that's going to go against I sub 3, so that needs to be introduced with a negative sign. The inductor's voltage source, if we increase that, that likewise will serve to impede I sub 3. Both of those terms now algebraically need to enter with a negative sign. We now have minus the quantity, minus 78 over 11s, and minus the quantity, 3 times minus 39 over 11. Or now we have our equation in matrix form, which is going to be this equation Z I is equal to V, and we want to now solve that for I. We could invert the impedance matrix. It's going to be an inversion of a 3 by 3 matrix symbolically, and then we could find rational expressions for I sub 1, I sub 2, and I sub 3. If we simply want to look at one particular current, in this case, let's say that we want to solve for I sub 2, one method to do that without having to invert that 3 by 3 matrix would be to actually take a ratio of two 3 by 3 determinants. So the numerator would be a 3 by 3 matrix that we would find the determinant of that matrix. The denominator would be formed by another determinant of a 3 by 3 matrix. And where are those coming from? Well, in our particular example that we had a Z that was 3 by 3. A1 is our, let's say, our first column, A sub 2 is our second column, and A sub 3 is our third column in our input, or I'm sorry, in our Z matrix. So here is our Z matrix, our impedance matrix, and this is now our source matrix. Using Cramer's rule, we now put the determinant of our impedance matrix downstairs, and in the numerator of I sub 2, we replace the column that we are trying to solve for, in this case I sub 2, which corresponds to the second column in our impedance matrix. We replace A sub 2 with B1 and find the determinant of that resulting 3 by 3 matrix. That's how we would then solve for I sub 2. It's a ratio of determinants. The denominator is just the determinant of our impedance matrix. So for our numerator expression, we're replacing the second column, that's the A sub 2 of the impedance matrix Z, with the right-hand column B sub 1 when solving for the second component I sub 2 in the vector of unknown variables. If we wanted to solve for I sub 1, then A sub 2 and A sub 3 would be the same in our numerator, and B sub 1 would be replacing the first column, and we would find the determinant of that. Our denominator would be the same. It's the determinant of our impedance. If we wanted I sub 3, we would do the same, except now A sub 1 and A sub 2 remain the same in the numerator expression, and we replace the last column, the A sub 3 column, with B sub 1, and compute its determinant. Again, that determinant would be divided by the determinant of the impedance, and that's how we could then, with three separate equations, solve for I sub 1, I sub 2, and I sub 3 if we wanted to use Cramer's rule. The main point that we want to get across is that we can now solve a complicated circuit problem. Again, just using algebra, the algebra will obviously now be in terms of polynomials or rational expressions in S, but we're just doing algebra and we don't have to do differential equation analysis. That's now the beauty of the S-domain circuit analysis. We can immediately, well, maybe not immediately, but we can step by step in a fairly mechanical process create an S-domain equivalent circuit, analyze that S-domain equivalent circuit, and then at the very last step, if we want to, we could solve for I sub 2 and inverse Laplace transform I sub 2 of S to find little I sub 2 of t, which would be the mesh current in that second mesh that we defined in this particular problem. That's the strategy of using S-domain circuit analysis.